Hi everyone, welcome back to lecture 4. In part 2, we're going to get into metamorphic rocks. So let us revisit our rock cycle diagram once more. When talking of metamorphic rocks, we are speaking about any kind of rock, sedimentary, igneous, or even previously metamorphic rocks, which have been exposed to enough heat and pressure to chemically or structurally alter them or metamorphose. And the overwhelming majority of this heat and pressure, which can metamorphose existing rocks, comes from the process of burial. If we take our rock cycle diagram and we look at starting with igneous rocks, we can see that as it increases in depth and is buried by successive layers, it becomes deeper and deeper where it is exposed to both higher heat and higher pressure from overlying burden. Same thing with sedimentary rocks. As more and more sediment is added atop and these sedimentary rocks cement and compact, more heat and more pressure atop the underlying rock, which can metamorphose them. Geologic metamorphism is specifically defined by changes in mineralogy and or texture of the rock. So what makes up that rock or how those components fit together. If it gets to the point of melting, if it's exposed to enough heat to begin to melt, once it gets to a certain degree of liquid concentration, it becomes igneous and is no longer metamorphic. And you may be thinking, well, if temperature continues to increase and increase as depth and burial continues and depth increases until it gets to the point of melting, becoming an igneous rock, would it before that point continue to become more and more metamorphosed? And the answer is yes. This is referred to as metamorphic grade. This is the degree of metamorphism which a metamorphic rock has undergone. So if it's only been under milder temperatures and pressure, it would be less metamorphosed than something that is very near the point of melting. That would be a much higher grade of metamorphism. So with an increase in temperature and in pressure, the metamorphic grade 2 increases. The higher the grade, the more dissimilar the rock is from its original version, or the more different it is from what it once was. And an increase in depth corresponds to an increase in temperature and pressure. Generally speaking, the deeper it is, the higher the temperature and the higher the pressure. As mentioned earlier, there are two primary ways that a rock can change if exposed to the right conditions, that being high enough heat and pressure. Number one is mineralogic metamorphism, so changes in the mineralogy or the content of that rock. This happens through atomic rearranging or chemical alterations in general. One process by which this happens is dehydration. As heat increases, we all know that if we leave a glass of water out in the hot sun in the middle of the day, we'll get condensation on the outside of the glass, and then eventually we'll see the water start to decrease, and that's because it's evaporating. If you get a rock up to high enough heat and pressure, the water molecules within that rock will too start to evaporate. And as that happens, other bonds are being broken, those bonds that those water molecules have with other molecules within that rock, and this in and of itself can create an entirely new rock. One example of this is the metamorphism of shale to a garnet mica schist. This would be a very high-grade metamorphism. It takes an awful lot of heat and pressure to get from a shale to a mica garnet schist. You can probably see that there have been a lot of changes just visually by these two images. Here we have a diagram displaying the metamorphic evolution of shale to a schist or gneiss. So if we look over here on the far left-hand side, this is the start of our timeline, and we'll start with shale, which is a sedimentary rock. This is primarily layers of clay stacked on top of each other, as we discussed in part 1 of the lecture. With increasing temperature and pressure, that clay will slowly convert to chlorite and mica muscovite, bringing us a slate which has a low-grade metamorphism. And we continue to increase in heat and pressure. Those micas and chlorites or mica muscovites and chlorite will turn into biotite mica and slowly to garnet, kyanite, silimantine, so on and so forth, which are both high-grade metamorphosed rocks. Schist and gneiss being more metamorphosed than phyllite, because that occurs from a higher temperature and pressure than does phyllite. It is also common to see a lot of feldspars in quartz. Those are both minerals that you saw in your mineral lab throughout. Most of these grades, however, it is harder to distinguish between these grades because they encompass so many of them. So when we're talking about classifying, we're usually looking for these sets of minerals. Again, while all schists and gneisses were once shales, but had been altered by temperature and pressure or metamorphism, they are most dissimilar to shale. So in this case, we would call shale the parent rock or protolith to slate, phyllite, and schist or gneiss. However, slate is going to be the most similar to shale, and schist or gneiss will be the least similar to shale because it's undergone the most metamorphism. So when asked what the protolith of a metamorphic rock is, it is simply what rock it used to be, or what its parent rock is. A few examples of parent rocks and their resulting metamorphic rocks are limestone. Limestone metamorphoses to marble. This is in part why marble countertops are so soft and can be porous and become stained, because they come from what was once primarily fossiliferous or stone composed of organic matter, like seashells and bacteria and so on. Sandstone can be metamorphosed into quartzite. This is why quartzite countertops are so hard and durable, because if we take a sandstone that is primarily made of tiny quartz grains, if you guys remember from your minerals lab, quartz was one of the hardest minerals that you looked at. The glass plate does not scratch the quartz. This is what makes quartzite countertops so hard and durable and also expensive. They're quite heavy as well, so it takes a lot of money and fuel to transport them. Basalt can metamorphose into amphibolite. You'll see an example of that. And then, of course, shale has a number of grades of metamorphose and products of that metamorphism. So different temperature and pressure conditions will yield different metamorphic products. We can take this diagram as an example. Up here on this axis, we have temperature increasing in this direction, and both pressure and depth, so P for pressure and Z for depth, increasing in this direction. At medium temperatures and low pressures or low depths, we would have a product of andalusite. And at higher depths and higher pressures but milder temperatures, we can get kyanite, maybe up to the medium-high range of temperature as well. And then on the opposite end, at both low and high depths, but only high pressures or medium to high pressure, temperatures, medium to high temperatures, and a range of depths or pressures, we can get sillimanite. You guys may have seen some really decorative and beautiful lamps made out of sillimanite crystals if you're walking around the right shops for it. And all of these products, andalusite, kyanite, and sillimanite, all have the same basal formula. So they have all of the same ingredients, but given different temperatures and pressures, we will end up with one or the other. These are referred to as polymorphs, meaning, once again, they have the same composition, but have different structures as a result of different exposures to temperature and pressure or depth. This is a function of atomic rearranging, the breakage of previous bonds and the formation of new bonds given the same material. There are a few different ways by which metamorphism can happen. Number one is contact metamorphism. This is metamorphism resulting from direct contact or nearly direct contact with a magmatic body. So when we talked about igneous rocks, we talked about plumes or other magmatic intrusions such as batholiths, dikes, sills. Anytime these are intruding an existing rock body, that high heat will manipulate or metamorphose the rocks that it comes in contact with. It essentially fries them. And this induces recrystallization, or in other words, that atomic rearranging we just discussed. Number two, we can have regional metamorphism. And this one's almost like a trick question because it can contain many types of metamorphism that occur over an entire region, hence regional metamorphism. So this generally refers to very large-scale topographic changes, so changes in the shape of the land, and is associated with tectonic stresses, so very major energy and forces. So this happens at convergent margins, where tectonic plates converge or come together. Divergent margins, where tectonic plates diverge or move apart. And orogenic belts, which for all intents and purposes are essentially convergent margins on steroids with a very high amount of volcanism and earthquake activity. Lastly, we have dynamic metamorphism. This is almost like a small-scale regional metamorphism. This is metamorphism resulting from small-scale topographic changes such as faulting or major cracking in the subsurface. Note that regional metamorphism can encompass both contact metamorphism and dynamic metamorphism. When an intrusive igneous body or a blob of magma or dike or sill, whatever it may be, comes in contact with existing bedrock because it is ejected and moves up towards the surface, it will metamorphose that surrounding bedrock or whatever it's in contact with at different degrees. So take this image, for example, where we have the hottest liquid magma intrusion. We have several degrees or metamorphic grades moving away from that because we'll have the hottest temperatures and the highest pressures because there's pressure building up from this actually being pushed into this space as well. So highest temperatures and pressures towards the liquid magma, and the coolest temperatures and lowest pressures farthest away from that. So we end up with these sort of bake zones or ringlets around that body. If it's a dike or a sill, it wouldn't be a ringlet, but still same idea. Of different grades of metamorphism. So in this case, if we have a magmatic body coming into a bunch of limestone bedrock, then at the highest temperatures with the highest degree of metamorphism, we'll end up with garnet and diopside, then a calcite and chlorite, and then lastly that marble. So the marble is actually one of the lower grades of metamorphism of limestone. This happens via recrystallization, and this system undergoes uniform stress, meaning that this blob of magma here will exert the same amount of pressure and heat over here on this area as it does on this area and this area. It's the same or uniform all the way around that blob. With recrystallization, we can see not only a change in mineralogy, but a change in texture as well. So if we continue with this sandstone example, if this undergoes enough change in heat and pressure, it will recrystallize into quartzite, but it will transition from a clastic texture, so the grains are cemented together by some precipitate and have been compacted or smushed together, into that crystalline texture that, like what we saw with many of our igneous rocks, where the grains or crystals are fused and interlocked together because they have grown into each other. Now within regional metamorphism, we may also see some contact metamorphism. Notice this example of a convergent boundary between continental crust and oceanic crust. The oceanic crust subducts underneath the continental crust, and as it gets deeper and deeper, it will eventually start to melt away, which will give us magma intrusions, and we will have contact metamorphism in those areas. Additionally, we will see some dynamic metamorphism right along the contact of the oceanic crust and continental crust because there's a high degree of pressure in this area, albeit low temperatures. But that pressure alone can be enough to generate some metamorphism at cracks or fissures, things like that, fractures. And we'll dive a little deeper into dynamic metamorphism momentarily, but the important thing with regional metamorphism is, again, that it can encompass several types of other metamorphism because it's considering an entire region, a region being a whole mountain range plus some of an ocean basin, some very large amount of space. And here's just another visual of the same idea, showing both that contact metamorphism and where a dynamic metamorphism would occur in this, what we call zone of intense shearing, or scraping past one another. Those two plates, tectonic plates, scraping past one another. There's going to be a lot of tension and shearing within that area, which in turn creates a zone of very high pressure and can result in metamorphism. And dynamic metamorphism does commonly occur in these shear zones. This is where the Earth's crust has ruptured from localized stress. So this would be similar to pushing together a clump of somewhat dehydrated putty or Play-Doh, where you would get a little bit of cracking at the part where you're exerting the most force, or localized stress, in other words, which would take place at the apex of that bend, so the halfway point of that bend. When we have a lot of these cracks in the Earth's surface at these points, it's called a fault zone. And this is where rock is pulverized by that intense pressure and some heat associated with that. Because of that shearing force, that back and forth, that rubbing creates a little bit of heat in that process from friction, much like rubbing your flat hands together when it's cold to warm them up. So this is a good point to go ahead and hit pause and take a quick brain break if you would like, and then we can get right back into it. With that, we can start to discuss metamorphic textures, which we touched on a little bit earlier with the sandstone and quartzite example, going from clastic to crystalline texture. But let's revisit the metamorphism of shale into gneiss or phyllite, both the high-grade metamorphosed versions of shale, shale being their protolith or parent rock. Let's look at some visuals here on the left-hand side, moving from shale all the way to gneiss and phyllite, changing that mineralogy, and with increasing temperature and pressure. When we're looking at the textures, generally we will see more changes in the visual texture with increase in metamorphic grades. So consider this image of the shale. It's kind of homogeneous, meaning it seems very plain all the way around. There's no necessarily striking features about it. If we increase to a low-grade metamorphosed version of shale, we now have slate, which you can start to see some lineations or striations, these lines or linear features, as a result of that low-grade metamorphism. Moving to a high-grade metamorphism, you can start to see some dramatically different features. These wispy, wavy lines of phyllite, quite very many of them, or a gneiss, something entirely different with these blotchy, globular, somewhat flattened-looking crystals all connected together. So just by taking a glance at the texture of a rock, you may not be able to identify it right off the bat, but you may now be able to say whether or not it's undergone a very high degree of metamorphism or a low degree, or maybe even none at all. As we discussed earlier, limestone will metamorphose into marble given the rate conditions, and this is a textural change rather than a mineralogical change. That's why marble is, again, somewhat porous and soft and fragile and can sometimes become stained over time because of the soft organic material contained in limestone or its parent rock. Now, to really understand metamorphism, we need to first have a good comprehension of stress and pressure. Stress and pressure go hand in hand. Stress is an applied force, and pressure is an amount of stress or force distributed over a certain area. So pressure is a stress over an area, and stress does not take area into account. The pressure in your car tires are in pounds per square inch, or PSI. The pounds is the amount of stress or force exerted, and per square inch would be the area. So that's what we're considering when we're talking about pressure. Earlier I talked about uniform stress with the example of contact metamorphism. This is in any case where the distribution of stress is equal in all directions. It is a common sight in contact metamorphism, but this can also happen during burial because we'll have pressure from overlying rocks atop, but also the pressure from whatever happens to be on the left and right sides of that body as well. Non-uniform stress is the opposite of uniform stress. This means that there are differences in the amount of stress applied in different directions. The principal direction of stress is the direction of the most force applied. And we can consider confining stress as an example of this. So burial can result in both uniform stress and non-uniform stress in the case that there's not a whole lot of confining pressure or things holding the sides of some body in place, and we just have things adding to the top weight of it. So we're putting more and more sediment or rock on top of some bedrock. Then the confining stress will increase, and the principal direction of stress on that body will be in the vertical direction because we're adding things on top of it rather than pushing it in from the sides. If we were pushing it in from the sides, then the horizontal axis would be the principal direction of stress. These non-uniform stresses can be broken down into 3 different types. One, compressive, so that's the pushing together. You are exerting compressive force when you are pushing and clicking together 2 Lego blocks. Second is tensional. This is a pull. So if you are stretching apart a piece of putty, that would be a tensional force. You're pulling it apart. And then lastly, shear, which we looked at a little bit earlier. Again, sanding a plank of wood would be an example of this because you're moving it back and forth across the surface. Some people call scissors shears or a pair of shears, and that's because the blades shear one another. They slide past one another to cut something. So let's go through a couple of examples together, and I'd like you guys to go ahead and play along. In the top left image here, we have some sediment being buried with increasing confining pressure from things being added on top of it, but also there's existing bedrock on the left and right hand side of it. So we have the same amount of pressure or force exerted on the vertical axis, top and bottom, as well as the horizontal axis, left and right, or from front to back. This would be an example of both what kind of stress, uniform or non-uniform, and specifically the type of stress. That being compression, shearing, or tensional. Give you just a second to think on that. This one would be uniform pressure or uniform stress because the pressure is the same all the way around it, and it would be compressional because it is being pressed all together. Now let's take this deck of cards, for example. We've pushed it to where one corner is leaning one way and another corner of the deck is leaning another way. This would be an example of what types of stress. This would be non-uniform, and it is shear. So there's some force in one direction and another force in the opposite direction, so that this deck has experienced shear force, which is why it is tilting at an angle. Moving on to the amorphous blobs in the bottom left-hand corner. What kind of stress are all of these examples experiencing? On the left-hand side, you have what it once was, and then on the right-hand side, you have what it is after experiencing that same force. This one would be a non-uniform force because all of that compressional stress is being exerted in the horizontal direction. And lastly, some more amorphous blobs. Different type of stress. What is it? This one is also non-uniform. It's in the horizontal direction, and instead of being compressional, it is tensional because it's being stretched apart. If we have recrystallization under non-uniform stress conditions, the crystals that are being recrystallized will actually orient themselves perpendicular to the principal direction of stress. In simple terms, that means in the case of, say, something compressional, if we start with a bunch of plain mineral grains in, say, a sandstone, for example, and then we compress it in the vertical direction, these grains are getting squished and smushed and elongated so that they are actually perpendicular and kind of flattened and layered up and stacked perpendicular or opposite the direction of the greatest stress. We can take same example, if we exert shear stress on it, then we're going to end up with something angular. On the left here is an example of a non-foliated crystalline textured rock, which has experienced metamorphism, or this a non-uniform stress realigning the minerals during recrystallization to produce this sort of perpendicular layering, which means, or striations, linear features, which in this case means that the principal direction of stress would have been horizontal because we have these lineations or alignments in the vertical direction. And these lineations or alignments, this particular texture resulting from that is called foliation, and we call those rocks foliated. A few more examples of that for you. Here is a mudstone that's the very fine grained black matrix with a bunch of other various types of rock pebbles in it. These were all once near perfectly round, but it experienced compressional stress in the vertical direction. And so now all of these once nearly spherical pebbles have been smushed and stretched out and elongated perpendicular to that principal direction of stress. Another example here, you can see that we have these striations, lineations, in other words, foliation. Foliation is the texture, oriented perpendicular to the principal direction of stress. Here's one last example. If we took something with very flat bedding that already had linear striations because of how the deposition occurred, so we had maybe a layer of clay, and then here sand, and then another few layers of clay throughout time, and we can see those horizontal transitions already. That doesn't necessarily mean that there's foliation in that, but rather those lines would be periods of deposition. But if a compressional force was exerted on this particular block of rock in the horizontal direction, we may end up with something like this, where we have now all of these striations in the vertical direction, in addition to the pre-existing bedrock layers, if we're considering this on a large scale, or depositional layers, either way. Now in sort of a wave format because it's been mushed into a smaller space. However, there is not always foliation in metamorphic rocks. When there is a uniform stress exerted on a body that is metamorphosed, the rocks will recrystallize with uniform grain size and uniform texture. Marble is an example of this. So if we look at this, you can see some crystalline outline. It's fairly amorphous. If we looked at a thin section of it, a very thin slice of that rock put underneath a microscope and altered, and the color is a product of altered light being passed through it, we can see that all of these crystals are interlocking together. They're somewhat close to around the same size, but none of them look smushed in any particular direction. You do see some lineations in some of these crystals, but those are a product of the crystal itself. So this would be one type of crystal, and this would be another type of crystal. So all of these purples are one type of mineral, all the blues are another type of mineral, and all these yellow or whites are yet another type of mineral, green, so on and so forth. Quartzite, further example of that, you can see the same case where the grain size is even more uniform. So in your mind, think uniform stress, uniform grain size. In your Metamorphic Rocks lab, you will get to work with a table similar to this. This may remind you of the table that you worked with for your Igneous Rocks lab. First, it organizes the metamorphic rocks by texture, so foliated or non-foliated. From there, we can consider the grain size, fine to medium to coarse grained. And then composition, which may be more difficult for you to tell, type of metamorphism, other comments, and then finally rock name. You won't deal with map symbols right now, but this is just another way that we can present these types of rocks in mapping format. Many people will overlook the comments section of these tables, or other properties sometimes it's called. I highly recommend that you guys pay specific attention to that. Sometimes those can be the difference between being very confident on your identification and not very confident at all. So to conclude, just a few reminders for you guys. You have a lecture quiz to complete on Canvas. This is over both Part 1 and Part 2 of Lecture 4. Secondly, you need to complete the Investigating Sedimentary Environments activity. This is meant as a study tool for you to use to prepare yourself for the first exam and the final exam as well. So it benefits you to include as much information as possible and to put it in words that you understand, not what you think would sound good to me. And then lastly, if you haven't already done so, finalize your previous lab from the last week and have a nice day. See you all next time.